Okay, well, thank you everyone to coming to our virtual community of practice here for the Wind and Water local scale group. We have three speakers today who are going to be kind of walking through what they have been doing that is adjacent to some of the SimCenter topics that we have been working on. And so just as a reminder, we'll be going for about 20 minutes per presenter. We'll kind of hold questions for the end, I think, and see how things go. So just you can use the Q&A window at the bottom of the screen and start doing some or enter in your questions. We will bring some of the questions to the full audience and others if you, as the presenters, if you've got time to kind of look at the questions and see what's very specific into the nitty-gritty of your own material. If you could just jump in and try to answer those questions, it would be very helpful. And so our first presenter today is going to be Dr. Nils Gosberg. Dr. Gosberg is from the Hydromechanics, Coastal, and Ocean Engineering Group at TU Braunschweig in Germany. He has been leading a team in the fields of coastal and ocean engineering and has revitalized some of their research facilities in the form of saltwater wave current flume there in Braunschweig and the large wave current flume at the Coastal Research Center Hanover. And right now he's leading the European Research Council's project Angry Waters, Scaling Fluid-Driven Processes for Building Collapse in Extreme Flow Conditions. And so today he'll be talking about some of his research, and Nils, the floor is yours.
Thanks, Mike. I'm quickly sharing my screen and then we are good to go. Just let me know if you see the shared window. Looks good. Looks good. Perfect.
Great. Thank you.
So, first of all, Mike, thank you very much for inviting me. It's a pleasure to be here and share some of the research we have been doing over the past 5-6 years. But I will focus specifically on what we've done in the last 3 years, partially during COVID. And I don't have to say anything more about myself. Thanks for introducing me. I've given my title, the talk title, Loads and Effects of Extreme Flow Conditions along Shorelines and on the Built Environment. And before I start off, I'd like to briefly acknowledge my co-authors over the past years, Clemens Krautwald, Hayo van Heffen, Jacob Stolle, Iwan Mister, Tomoyo Shibayama, and many more. Why is that not there? Now, the agenda is threefold for today. Brief introduction. Then I have 3 different parts of research that I want to present that all use large-scale experimental modeling. And then there is a summary on some conclusions I've drawn from our research. And the photograph that you see here is taken from a field survey that I attended in Japan in March this year. For some of you who don't remember what was on 1st of January 2024, there was a Noto Peninsula earthquake and tsunami, and I want to use that to motivate and introduce some of the research we are doing. There is a new paper coming up by Inagaki et al. That we co-authored that is about that field survey, and you see here the location of the Noto Peninsula, the Toyama Bay inside, and you see the rupture process here along with the main shock was in a magnitude 7.6. And when we were in the field, we found severe damage in various places, in particular on the east coast of the Noto Peninsula, nonlinear interaction with existing coastal structures. So some seawalls that shielded the coastline and the built environment, while other parts really let the wave fully impact on the buildings. And what was also surprising to us, there was fairly little fatalities and soft measures, which are very well trained in Japan, like awareness and early evacuation, probably did their share in that. However, it was tremendously interesting to me to see the damage pattern, the local effects. And these, I think, are very important for modeling. So I want to share with you 3 pictures in the next 3 slides. First of all, This is a picture of Cerro Maru city on Noto Peninsula. This place had 3.9 meter inundation. And look at, which I think is important for modeling of fluid and structure interaction. The ground floor was fully, everything was blown out. A wave went through pretty directly and caused, I think, a lot of debris. Next one, we also saw dislodged parts of houses and structures, sheds and so forth. And what was also interesting was that this waterway made a pretty interesting pattern of inundation progress. So it was not like a just straight line, coastline, but the wave could enter through this through this river kind of canal further into the city and cause some damage further inland. Next picture taken at Yucay fishing port. I think this fishing port was also in the media quite a bit. What you see here, for example, is where the wave came from left to right in that case, and led to some elastic or plastic actually deformation of that production facility. And you also see a top-down house that was residential building before, pretty much intact, but upside down, and then it hit into that production facility here. Last picture, and this is something we observed very, very often. Wooden houses dislodged from their foundation. Foundation is here, and what we usually saw was that the bottom sill of these wood frame houses would just remain in place, and there was a concrete foundation, and then the entire superstructure, it is this one here in that case, was just dislodged and pushed into the next building row. So all of this, I think, is pretty important in terms of tsunami modeling. So the quick section summary, the field evidence is important, and it needs much greater attention in order to bring what we find in the field into our labs. And the built environment is far more diverse than what research currently covers. That brings me to the first bit of research I wanted to share with you, and that is using our large wave flume in Hanover to produce broken solitary waves. And what you see here is a picture that's just downstream here in the very end. You see the wave maker, and in the back of that photograph is a composite bathymetry that you will see next. So the research was motivated by this kind of setup here. Consider a very steep mountain and a landslide, which results in a short tsunami, not the type of earthquake-generated tsunamis, but something rather short. And we wanted to model the composite bathymetry consisting of a sloping beach and then a horizontal plane. Method-wise, we used, as I said, the large wave flume. And in terms of producing the hydrodynamic features, we used a solitary wave that, by climbing up the slope, at some point broke close to the edge here, and then propagated as a broken horizontal flow that was impacting then some buildings and features. Very quickly, this is about a minute video that shows you what the facility is like. A large wave flume, or large wave and current flume, since a year ago. It's a facility that is, and we are flying now through, it's 300 meters long, 5 meters wide, and 7 meters deep. It is equipped with a wave maker at one end. You see it here in action, 7.5 meter stroke. It can generate 3 meter wave heights, and it's servo motor driven and has an active wave absorption. Two other main features of the flume is, first, a current generation system that can either generate following or opposing currents with respect to the waves. It is about 20 cubic meter per second discharge to generate a flow of maximum 1 meter per second. And last, we can also equip or put some structures into the flume in the so-called deep section. It's staggered 2 meter deep in most parts, that you see up here, and then it's up to 6 meters deep in the deeper deep section. And we use this facility to do the research that I'm presenting today. Now, back to the research of Hajo van Heffen, the PhD students who led the work. I want to show you a video of what the wave looks like. And you will see when I start the video that the wave is starting from here. So solitary wave shortly before it breaks. And I let the video run. You can see the breaking process. And then after breaking, you see a sustained flow that is resembling a tsunami on-land flow in our flume facility. Just a couple of examples of the flow depth, surface velocity, and momentum flux. And some of these quantities we derived with sensors, wave gauges, but the surface velocity was derived from overhead cameras, like this one here. Images were stitched together, and then surface PIV algorithm with popcorn from a cinema was used at very large scale and produced these kind of surface velocity maps. And if we then just look at 3 different locations here on the right-hand side, you see the time history of the flow depths up here. So for that particular test case number 6, up to about 20 centimeters in the maximum, the surface velocity at 3 different locations. And you see this is not coinciding with the maximum water depth and the resulting momentum flux that you see here. And it's also clear there is no coincidence between either maximum flow or water depths in that case. Because this was also complex over that horizontal surface, we came up with some prediction equations that are summarized here in the publication, both for the flow depths first equation and the maximum momentum flux second equation. And you see that both are dependent on the nonlinearity of the wave, the freeboard, so the elevation difference between the mean water level and the platform elevation, as well as with the coordinate x, that is the distance between the edge forward motion of the wave. So quick section summary. The large-scale facilities helps us to produce data sets to model tsunamis and to also provide data sets for verification of numerical models. We have to admit, though, that the broken solitary waves in many cases are too short if we look at earthquake-generated tsunamis. For that, I'll show you something at the end of my talk, what we are doing or planning to do with respect to these longer hydrodynamic events. Next part of research is about extreme flow conditions and building specimen, and this is built based on 2 publications by Clemens Krautwald, another PhD student of mine and now postdoc in the group, who looked at the same hydrodynamic conditions that I showed before, but now interacting with buildings. And this was motivated by the observation that in the field we often do see collapsed structures, or we do see elevated structures where the flow is having very different flow pattern than what we usually see. And if we look at the wooden buildings I showed in the beginning in Japan, there are still several knowledge gaps, in my opinion, that is with respect to the debris production and evolvement over a plane, and also with the momentum transfer. And if we look at elevated buildings, we also have this uncertainty about what happens if the building is partially elevated from the ground. And this has also some uncertainties with respect to uplift, loading, and so forth. Same flume, large wave flume, 2 photographs of the specimen and what it looked like. You see here a slap-on grade configuration on the left, and then an elevated configuration with 10 centimeters above the floor. You see pressure sensors, the whole structure, and I switch to the next slide. Full structure was on a multi-axis sensor for the load measurements. We had a couple of wave gauges and also ultrasonic distance sensor for getting the water depth close to the structure. difference between slab-on-grade and elevated structure. If we look at further offshore location, we don't really see a difference. And this, I think, is not surprising. There is no immediate effect on the building with respect to offshore locations. But it starts to getting more interesting if we go closer to the structure, and you see that a little further away, it is actually the case that there is a little bit more water depth for the elevated structure. But when we go very close to the structure, we see that's a slab-on-grade structure where the flow can't go underneath the structure. It produces a huge splash up of about a meter 10, and a totally different time history of flow depths close to that location. And if we go on the other side, backward side of the structure, we see that there is also a big difference with respect to the splash up that happens when we have the slab-on-grade structure. So very diverse flow pattern and spatial distribution, also temporal distribution of the flow depths. So now if we go and look at the different processes, slab-on-grade at the top and elevated structure below, you see that there, through this gap, this flow can just pass underneath. For the slab-on-grade, we see that there is a horizontal pattern of flow redistribution and shielding of the buildings in the back. And all this is, I think, very important with respect to the second and third row of buildings that are close to the coastline. Last, let me just say a few words about structural collapse, because that was what the second publication was about. I show you 3 videos of 3 different collapse processes, which we were able to identify in the publication number 2. First of all, there is one where the front studs of that box, and now you see that the box is really scaled such that it can collapse. Front studs were giving away. And if we look at the video, you will see that the wave is coming in. It's a little bit slowed down. First of all, you don't see much. Then you see wave is breaking into the front, hitting the back wall, which is then also pushed out, and the roof is failing. And you see quite a bit of debris production towards the right-hand side. Next collapse process that we identified was an insufficient transfer of tensile forces, in particular here at the backward side with respect to the connection between the back wall and the roof. Quick video to show you how that looked like. Roof is giving away, it's split in 2, and then you see again the debris production downstream of that wave. Last, a change in the structural support system, and I think it's best explained if I show it this way here. You see a rotational motion once the collapse is initiated. You see that it's rotating torsionally around its vertical axis. Less debris produced. Some of the parts are still hanging in here, and yeah, this was also a process that we observed a couple of times during the experiments. Okay, section summary: modeling collapse is possible. However, scaling considerations are still a frontier that need to be tackled next. Last quick 2 slides, and I'm done in 2 minutes, Mike. I hope this is okay. So what is next? The avenue for the research program that is coming. The predominant problem, in my opinion, is that we need to simultaneously scale hydro and structural processes, which is a big frontier, in my opinion. And we also need to understand and compare physical experiments at different scales. So say in mid-scale facilities and in large-scale facilities. This so far has not really been addressed in research, and a requirement for this kind of question and answer to the question is you first of all need to have equipment that you have equipped in a mid-scale and a large-scale flume. So what is going to happen in the large wave flume is that we are purchasing a big dam break gate, which will be able to impound 3.3 meters of water depth. And it is a swing gate, as you can see here in this little sketch, and it will open in about 2 seconds. And then we are able to compare large-scale testing with the smaller scale dam break gate that we have here in our institute in Braunschweig. And that allows us to cross-compare different scales and try to understand what happens. And all this is necessary for the research project that Mike already announced in the beginning during the introduction. It's the research project Angry Waters, a 5-year program at Technische University in Braunschweig and the Coastal Research Center. Its title is Scaling Fluid-Driven Processes, Building Collapse in Extreme Flow Conditions. And our ambition really is to achieve a breakthrough in modeling these multi-scale and multi-physics processes, such as building collapse, using novel scaling laws. And these are supposed to be on the basis of Lie group scaling. So, summary and conclusion. I think what I try to show today is that combined modeling of fluid and structure processes are possible. It's feasible as long as you have appropriate facilities. And the challenges, as I said before, are in particular in scaling tradition and the strategies between the different fields, structural engineering, hydraulic engineering. And aside from the physical modeling, I think there is a big need for advanced numerical models, both for multiphysics and multiphase, as well as for more efficient fluid structure interaction. And with that, I'd like to thank you for your attention.
Well, thank you very much, Nils. That was very interesting stuff, and I think it motivates kind of why we're here really well. So if you have questions specific for Nils related to his presentation, if you could drop them into the Q&A chat, and we will moderate those as they come along. For the sake of kind of efficiency here, I think we're going to jump into the next presentation, and then we'll have discussion towards the end. And so, Barbara, if you would mind going second here, and we will jump right into that. And so while you are finding your presentation, I will introduce you here. So Barbara Simpson is joining us today from Stanford. Barbara is an assistant professor there at Stanford, using advanced computational and experimental methods to characterize structural response. And so what she's been working on is developing innovative structural systems for building performance, reducing the effects of natural hazards on the built environment. And so today she'll be talking about one of her projects related to that. And so Barbara, if you want to dive right in, we can get going with that.
Sure. And actually, I think I'm glad that the presentation went before this, because a lot of this presentation is going to deal with similitude laws specifically for fluid structure interaction. So our group has been sort of thinking about this a lot. Most of us are from the structural discipline, and we are now starting to do a lot with fluids. And so from our perspective, the structure usually is paramount, but we've been starting to ask this question of, when does this FSI effect matters? And I'll just briefly go through what I'm going to be talking about today. So I'll sort of go into the motivation, which is just this idea of having small scale experiments and simulating these systems that are subject to both fluid dynamics, but also potentially structural dynamics. And then I'll go into some applications that we've studied so far, the unique data that's been generated from that, and then ultimately sort of posing the questions that will get some brainstorming going in this session. So let's start out with this motivation. The idea is this: if we're going to use our experimental facilities, we're constrained by their scale and their capacity. So, if we're looking at structural components, maybe we could simulate them at full scale. If we're looking at the scale of a building, then we have to scale down. And then if we look at sort of these regional models, we have to scale down even further. And usually when the scaling occurs, you're typically scaling the fluid flow, but sometimes or oftentimes the structural dynamics is neglected, or maybe it scales incompatibly with the fluid flow. So it sort of leads to this question of the simulation paradox, is that we really need this physical model data to validate our computational numerical models. But these physical models may not represent full-scale structural response of the actual structural side of the system. And I'm going to hone in this on a very specific infrastructure type that NSF actually does not fund, but that's going to be the floating offshore wind turbine. And that's just because my group has done a lot of work in this area. And it's really subject to this simulation paradox. And so it's a great example. So floating offshore wind is a great example of a multi-dynamical system. It's subject to aerodynamics from the wind, hydrodynamics from waves, and then you have the structural dynamics involved with the tower, the blades, the rotor that actually rotates, the mooring dynamics that keep it anchored. And then actually you have controls that move the rotor and turbine to actually align it with the wind loading. So there's a lot of interacting effects going on here. And luckily, if you're looking at, say, 10 megawatts, which is what's supposed to be the estimated floating offshore wind turbine that they're going to be building off the Pacific coastline, they're 100 meters tall. So they're incredibly large structures subject to a lot of interacting effects. So when we think about scaling to look at them in terms of our experimental tests, we want to scale them in geometry, but we also want to scale them in terms of dynamics. And that basically means that, the relevant forces are scaled appropriately. The issue with that, when you have all these sort of multiple dynamics involved, they don't necessarily scale together all at once. So here's just an example of potentially scaling the wind with respect to the Reynolds number, the structure with respect to the inertial and elastic forces, and then the waves or hydrodynamics with respect to the Froude number. And I'm not saying that these are the numbers you should choose. This is just an example. And so if you look at a system that's subject to wind, wave, structural dynamics, and you sort of look at that in terms of time and then length, so geometrically scaling down the structural system, you can clearly see that there's some incompatibilities between the governing forces, especially when there's multiple governing forces involved. And so, there's a lot of these wind wave facilities all over the country and across the world. And not only do they have a difficult time just getting a nice control volume near the rotor itself, you also just have the wind and the waves aren't scaled appropriately. And so many have suggested a number of ways to mitigate that. Here's an example on the left. So what you can do is you can actually geometrically distort the wind turbine to get perhaps the thrust forces that you're interested in. And so then you can sort of mimic the waves and wind to be roughly similar. So that's something that we could also think about in the natural hazards community. And then, of course, the other side of that is maybe you just take your wind-only experiments, your wave-only experiments, and then you combine them in a numerical model, which then can operate at full scale, but then also comes with extreme computational expense. It's not necessarily clear that it's been validated if the experiments are only focused on one of the governing forces. And so we get back to this simulation paradox question. It's that we need this physical data, but it's not exactly clear that whether it represents a realistic response of these structural systems because everything's done at model scale. And so what we've proposed is an online testing method, also referred to as real-time hybrid simulation. It's a testing method that's been around since the late 70s, early 80s, and more recently, because we've just gotten so much better at computing calculations very, very quickly, we can now do these types of simulations in real time. And so what we can do is we can take this system with this coupled wind, wave, structural dynamic effects, and we can split it into two portions. So for example, here we have a numerical portion that includes some of the structural dynamics in wind, and then we have a physical model that maybe includes some of the structural dynamics, maybe not, but also includes the hydrodynamics physically. And then what we do is we use actuation and sensors to ensure that we satisfy equilibrium between the two systems, as well as similitude compatibility. So in this way, we could scale the governing force that we're interested in all in the experiment, and then we can have that model interact with a full-scale system that has the remaining dynamics. And so we've used this for a number of different applications. The first one is just sort of a tsunami loading or solitary wave loading on a bridge pier, just as an example, so that we could sort of test whether this worked or not. And just something to note is that, again, the bridge model can be at full scale, and then we basically have an actuator that scales down displacements, sends it to the physical model. We measure the corresponding forces, and then that updates the numerical model. And then that all has to be conducted in real time, mainly because we can't slow down the fluid. So synchronization between these two portions is paramount. And so we've done that for cascading earthquake tsunami effects. We've managed to do it sort of on a three-span bridge where we can duplicate the wave loading on two bridge piers. We've actually even damaged the bridge prior to the tsunami loading to sort of mimic cascading earthquake tsunami effects. And that was a test that we conducted actually in 2020. Since then, we've broadened the applications that we can address. We've looked at monopile offshore wind turbines, where we've sort of partitioned out the soil effects, potential soil effects, as well as wind loading in a numerical model, and then that interacts with the physical model, including the hydrodynamics. We've also done it for a floating case, like what you see here, where again, the wind loading is numerical and applied via a robotic arm in the physical experiment. And finally, something that we're doing right now is virtually deepening the wave flume at Oregon State University. And so you can imagine that you use a series of motors and or cables to emulate mooring lines that are significantly deeper to sort of represent what's happening off the Pacific coastline. And so we have a lot of data. And so then it becomes this question is, so if you have data that now includes fluid structure interaction effects, what do you do with it? And so here you can sort of see differences. This is for the floating case of including the wind along with the wave loading. And so in some cases, we just hold that turbine fixed and just let the waves sort of crash into it. In other cases, we just let the wind turbine just follow the wave loading. And then in another case, we actually add that wind loading. And you can see that, of course, the wind loading, which applies, sort of an additional effect, and the fact that the system is floating, it does move the entire system in a quite substantially different way when you have all of that acting together. And so let's just take a step back and think about what we could do with some of this test data. So something that we could do with hybrid simulation is we could think about how the structural dynamics affects the fluid loading, be it either with a two-way effect or via a one-way effect, depending on the degree of coupling between the wave loading and the structural dynamics. And so what we did is we sort of emulated a single degree of freedom system model. And here you can see this black line that's sort of representing the structural dynamics due to a solitary wave, which then if we sort of play around with the similitude distortions, we can get the structure to interact with the wave in different ways. And depending on the frequency of that structure, we can actually get this sort of double peaked structural dynamics effect or oscillations that occur during the duration of the wave loading. So, you can imagine using a system like that to actually study the degree of which structural dynamics starts to matter. And then you could, of course, try to emulate it with, say, some sort of simplistic, here's just a triangular pulse loading, sort of mimic that effect in, say, a mid-fidelity way that could then be useful for codes or something similar. We've also sought to understand it via higher fidelity models. So this is a model using SPH, where we've actually managed to mimic the case where there is no structural dynamics relatively well. We're starting to look at the case with structural dynamics too. And you can see that very much depends on the degree that you model the actual fluid itself, with, of course, computational time increasing the more high fidelity your fluid model is. And so you can see that, as you change the resolution of your fluid, we go everywhere from 2.5 minutes where not really representing the pressures as well at all in the experiment, to something like 8 hours being sort of the best case, and then 20 hours being a very high resolution model. And so that leads to this sort of last component that we've started looking at, is that given the computational expense of these models, maybe we should think about emulating them in a slightly different way, given you have enough experimental data or high fidelity data. And so in this case, we're using the particle finite element method that was developed by Minji Zhu and Michael Scott at Oregon State. And we're sort of thinking about how can we model the fluid, say using a graph neural network to represent some of the characteristics that we're seeing in these numerical models. And then once trained, hopefully those models run significantly faster, and we can start looking at things like uncertainty propagation, or risk, or whatever the case may be, given that the model runs significantly faster. And so that leads me back to this question: when does FSI matter, and how can we think about it in terms of this simulation paradox? And that you're scaling down all of these forces, and they're not necessarily compatible with one another. And so, just what I've been looking at in the previous slides is if you have a physical experiment, maybe you can just look at just the waves. You might be able to look at waves and wind if you distort the geometry. And then this hybrid simulation approach then allows you to virtually expand upon the dynamics that you're able to address. And therefore, you can think of that sophistication of the simulation being increased. But I just want to be clear, that does not mean that this simulation represents reality either. So, I love this quote that I'm sure everybody on the call has heard. So all models are wrong, but some are useful. So a lot of what my group has been thinking about is we're doing these very complicated things and coupling numerical models with physical experiments. But when do you need that? When does the fluid structure interaction effects matter? And that in itself is still a model. So how do you validate it? And so I'm just going to list a couple of questions that again hopefully spark some brainstorming and discussion. But thinking about validation of these systems is kind of difficult, because if you have physical experiments of, say, one or a few of the governing forces, then you might have hybrid simulation on the other side of that. But the hybrid simulation also involves a numerical model. And in the slides before, I've shown it of the wind. And so how do you make sure that that wind is actually modeled appropriately, or if the structural dynamics are involved, how do you actually validate this coupled experimental numerical model? And so you could imagine doing sort of high fidelity subsystem simulations of portions of the full system. You could think about also having surrogates involved to sort of look at differences between all the models. You can leverage some of the advances that have made by the Department of Energy in terms of exascale simulations. And then, of course, everything gets cross-validated against each other. And hopefully you converge on something that's about right. So validation of these systems becomes complicated because you can't rely on just the physical experiments of one force to validate other parts of your system. You kind of have to use sort of full system models for a select few cases, maybe mid-fidelity models for more like non-extreme cases, and then you have to combine them all in something that gives you an appropriate validation data set. These things also take a lot of expertise in disciplines that aren't necessarily classic civil engineering knowledge domains. And so, like, for example, we had to learn a lot about robotic arms to implement this. We also had to so the robotic arm could sort of emulate or follow the wave loading a little bit better. We actually used a lot from again, our background's not fluids, but we use linear wave theory to sort of enhance the control scheme of this system. So there's a lot of expertise that needs to be sort of embedded into these types of simulations. And even more than that, you get to this question of fidelity. So now you're adding more components to your physical experiment. And so, ideally your actuation scheme, your sensor measurements would all be sort of invisible to the loading. But you have to have a very, very robust responsive control scheme in order to make that feasible. Here's just an example here where the pink line is us just putting the specimen out there running waves, and then the blue line is us trying to follow it with the robotic arm. And you can see just by the fact that we have this robotic arm, we're actually adding dynamics to the system. And so, you know, you have to do a great deal of care to make sure that the data you end up with, even though it's supposed to be better, actually is of the fidelity that you're after. There's also this idea of what is the extent of this FSI coupling effect. So, you know, for example, here's an elevated structure that's subject to wind loading as well as wave loading, say on the East Coast of the United States. And, you know, typically we would experimentally model these two loading types separately. But we could think about perhaps maybe the wind and the wave, maybe there's an interaction coupling effect that happens there. And so maybe we would like to consider two-way coupling. And then, you know, there's the actual effect that these forces have on the structure. And I think there's still an open question on how much that effect is one-way versus two-way. So what we've been seeing in a lot of our experimental data is even when we hold our structure fairly rigid, it still tends to vibrate, which does affect those peak pressure coefficients. And so there is this question, how much does the deforming structural characteristics actually matter within the loading? And I think, you know, common sense wise, we often say like, oh, the structure deforms so little, it doesn't really matter that much. But there are definitely regimes where it might matter more often than other regimes, and we need to identify what those regimes are. And then, you know, for the case, how am I on time? Am I just, I kind of got distracted. Am I just?
You're good for a couple more minutes. Yeah.
Perfect. Okay, I'm ranting. And so, so a regime where this matters a lot, for example, is the floating offshore wind turbine case, right? Where you have this let's call it subsystem C, that's representing the wind loading on the rotor. It also is representing a lot of the controls that are happening to sort of move this rotor in place. That's then interacting through the tower dynamics with what's happening at the platform and the hydrodynamics, which might also be interacting with another subsystem at the seabed floor, which includes the anchorage, the soil effects, the mooring lines. And so in this case, the interaction components might be quite large and become even larger as these systems undergo more and more extreme wind wave loading conditions and displace a lot more. But then going back to the previous slide on the elevated house, maybe that doesn't matter so much until you know, you get an opening that appears in your structure, and then it matters a lot. So there's sort of these regimes that I think we as a community need to be clear about when these interaction and coupling effects become two-way versus one-way versus we can just model them separately and superimpose them and it's fine. And so this last slide, I think, lead very nicely to the previous presentation, is that a lot of how we do these sort of hybrid simulations is that we take our numerical model and we apply some sort of similitude law to it. So we assume that our hydrodynamics, for example, are governed by Froude number, which is for open channel flow. But as we get these sort of wave breaking processes, it's not exactly clear whether that similitude is actually appropriate for something where where something that's significantly different than just the gravitational forces and inertial forces. There might be other sort of phenomena going on here. And so just thinking about, again, if we're going to use this type of approach to generate unique data, where is that data not necessarily appropriate? And with that, I'd just like to acknowledge a number of different funding sources that were involved in a lot of the projects that you just saw. A huge number of collaborators, and then of course the people who actually do all the work and make this happen, the students and the postdocs, and then other collaborations that have offered ideas or inspiration for any of the work that I've previously described. And with that, maybe I can end and we can go on to the next speaker.
Yeah, I think that'd be great. Thanks so much. That was excellent stuff. I think we've got a lot of food for thought. So before Andrew jumps in here, Andrew, if you want to start sharing our third presenter, we do have two questions in the chat. I'm monitoring the Q&A. I'm monitoring. I think they're both good questions for the general discussion, so I will hold them both for the end and kind of let us pick that up, because I don't want us to shortchange, I think, what are important questions on that. So Justin and our other questioner, we will get to those after Andrew's presentation. So thank you very much, Barbara. That was very enlightening for us. And so Andrew, if you want to go ahead and share your screen, I can go ahead and introduce you. So our final presenter today is Andrew Winter. Andrew Winter currently works with Siemens software suite. So someone from commercial side of things, and I thought it would be interesting to get that perspective for us today. And so he's been working in support with Star CCM Plus for CFD and SimCenter 3D for FEM analysis, looking to simulate a wide variety of physics in both civil, aerospace, mechanical engineering stuff. He teaches some structural analysis courses at University of Washington as well, and has been very active in working with students recently on various natural hazards modeling concepts. And so Andrew's going to talk a little bit about some of the stuff he's been doing and how it relates to what we've been talking about here today. So Andrew, the floor is yours.
Okay, thanks, Mike. Everybody hear me okay?
Yep.
Great, okay. Yeah, so gonna give a brief introduction, although Mike took care of most of it. And then I got 3 different things I am gonna focus on that I've been doing that are FSI related, that are part of or at least, somewhat related to the natural hazards community, although that's difficult to do with my job now. So yeah, first project's going to be something from my PhD a little bit, and then from another PhD student of Mike's that I helped advise, and then a current project that Justin and Nils and I and Felix and a number of other people that maybe have been mentioned already working on. Let's see, this is my screen changing here. There we go. Okay, so I graduated from the UW in 2019. With 2 degrees. I work for Siemens now. As Mike said, I support FEA and CFD. It's a great opportunity. I totally recommend it. So my first project is tsunami-like wave impacts on coastal structures. Worked with Mike and Mark on these articles mostly, although there's a wide array of OSU-related and other UW-related collaborators. What is this project focused on? Well, we worked on a tsunami impact of coastal structures, thinking about the Cascadia subduction zone as an impending threat for a magnitude 9 earthquake. And the main thing we focused on was some effects that we looked at in the ASCE 7 provisions, or rather commentary at the time when it was 716, about shielding and channeling of fluid between more offshore structures, and then how that impacts a more onshore structure. So here the flow blockages in the test structure are the more offshore and onshore structures. And these are some tests from back in 2011 and 2015 and 2010 that did everything more or less symmetric. The 2011 test had some asymmetry to it, which was interesting, but we wanted to kind of push that more with this study and really dive into that and assess how much it affects these behaviors. So we went down to OSU back in 2017 for the experiments, using the large wave flume there. And we had a wide array of instrumentation. We have ADVs for velocity, ultrasonic wave gauges for wave height, pressure gauges, and some small load cells inside the structure, as well as large load cells outside the structure to get XYZ forces on the whole body. And then we studied an array of different structures where we have the wave hitting this concrete block, which was our neighboring more offshore structure, and then our steel test structure was farther downstream. And so we measured the loads on this for 2 different wave types. We did a broken wave and an unbroken wave, although the truly more tsunami-like one is really the broken wave. So that's what we chose to focus on after the fact, even though we had a large amount of unbroken wave data. Let's see, get this to play. Skip ahead a little bit so you can see the interesting part. So this is one of the broken waves impacting the test structure. Some of you may have seen this before, but if you haven't, it's pretty cool. But this is what we were trying to mimic with open foam modeling after the fact. And you can see the big difficulty here numerically is this free surface. Is this really a smooth free surface? No, this is a giant mess. So trying to use VOF, volume of fluid method, which really needs a smooth surface and a very, very fine mesh to do this kind of thing, is maybe not the most ideal, but on average, it still works out pretty good, is what we found. So you might think SPH or NPM or something else would do better with these giant splashes, but traditional CFD finite volume methods can still survive and get you good results. So these are our experimental results. We got a pretty good match between the load cell and the pressure integrated over the surface, the green and the purple curves, for all the different cases. And for all cases, both were well within the range of variation from test to test, the gray curves, of which there's many superimposed. And you can see the kind of the effect that moving the block from the wall towards in front of the structure has. You gradually, for case D, you get a massive reduction. For case F and E, you get kind of asymmetric reductions, in case B as well, and especially C. And some amplification as well, right? Like case F has very high force on one side, but very low on the other. And if you're wondering why the graphs look a little funny compared to the images, they're flipped. This is left over from my PhD defense. So the left and the right are flipped from pressure surface to orientation of the blocks. So we compared this to the blockage ratio provisions in the code, where the blockage ratio is limited in a certain range, but we expanded beyond that. We went to higher values, and we showed that for cases where you don't have any like blockage of the structure, C, D, or A, B, and E, things worked out fine. But when you have severe blockage of the structure, C, D, and F, you get way, way lower results than the curve in the code provides. And this makes sense because it's not really attempting to handle such a scenario. So that's why we were trying to expand our, make a model go beyond this. So we used OpenFoam as our CFD tool for this to try and model the fluid flow around these blocks. And we used, it's a finite volume code, Reynolds average Navier-Stokes, but not like the steady one, the unsteady one. So you can actually have variation in time. And we used add-on wave generation package, OlaFlow, by Pablo Aguirre, which is a very helpful tool. And then I'll talk a little bit more about the turbulence modeling in a minute. And the meshes weren't that big. They're only 4.5 million, which by commercial standards is nothing. That's pretty tiny. Maybe in research world, it's big, but yeah, you can run a lot of those very fast on a big cluster. So we did a lot of experiments with Reynolds stress models, K-omega models, and Reynolds stress models, and found that the K-omega SST model performed the best out of all of them. And this is pretty in line with industry as well. It's one of the most popular ones to use because it handles flow separation very well. It also doesn't have the same problems that a lot of K epsilon models do, where it builds up spurious turbulent kinetic energy in stagnation zones, like say on the front of the structure where the wave is running into it. That could be a big problem. And we found that was true for the standard K epsilon model in the bottom left. You can see the green curve is way higher than it should be. And that was very mesh sensitive. So the K-omega SST model was not mesh sensitive in the same way and gave good results, both in terms of timing and in terms of the peak value. The Reynolds stress model could have done better if the initial condition was probably better, but at the time, the initialization I was giving it was perhaps not the best. A better Reynolds average Navier-Stokes initial state could certainly help, but that's sometimes difficult to do. So this is what we ended up getting in terms of our simulated flow behavior. My video will play. No, okay. Well, that's too bad. I'm not sure why the embedded video is not playing. tested it beforehand. Anyway, let's try the next one. Here we go. So this is the wave coming in and slamming into the structure. And you can see that's not nearly as choppy as the actual experimental video, right? So you get a more averaged out smooth flow by doing this volume of fluid method, where you have a fixed Eulerian grid that doesn't refine itself. You could use adaptive meshing, but we found at the time that adaptive meshing was not at all necessary to get the quality of results we were getting. And as you can see, the open foam results match the experimental results quite well. The green curves are all lying within the gray band of values, and the peaks match pretty well as well. So what we did with this data was we expanded it. We did a lot of, we did a parametric study. We did a lot of different values of positions of the neighboring structure, the NS gray block here, and we were trying to quantify a blockage to get an effective force ratio that kind of reduces based on the position of the block and its proximity to the design structure, we called it, that would be experiencing the load due to the flow channeling or shielding. And so this is basically just kind of doing some geometry to figure out how much of the channel width should be chopped off and put into the calculation of the blockage ratio. And so we did a bunch of different cases here. You can see ranging from lined up exactly to against the wall, and we moved them near and far away along the channel as well for well over 200 to 300 cases in total, I think. And also varied the width of the channel as well, just in case the finiteness of the walls was potentially an issue, which we found out it didn't change things very much. We got basically the same optimized values here for where we were trying to optimize the width of that wake in this model and the length of it as well. The DW and the LW were being multiplied by the size of the structure to get the actual value. And so that's what we came up with, doing a least squares error minimization. And the resulting curves are not bad. They match the black dots or the open foam results with the calibrated model. The dashed lines are each component of the model. They get multiplied together to produce the red curves. And you can see that it works pretty well, I guess, is the the conclusion I have here. And currently, I am trying to use some of my old data from this and take it and remodel it with SimCenter 3 or StarCCM Plus. And my first attempt, which is not super refined, came out pretty darn good, which I would say the amount of effort I put into this compared to open foam was massively smaller. I think I spent an afternoon setting up a model, submit it, checked it the next day, versus several years of trying to master open foam. So I think the user friendliness of StarCCM Plus and the robustness of the built-in models definitely is a huge benefit to consider for the community. Some current stuff that's been going on, or more recent rather, we worked with student Nikki Lewis, and Justin contributed to this as well with some results along with myself. And she was looking at coupling open foam with open Cs using the precise coupling library. You can see here she was doing an FSI coupling loop with the precise tool being sort of the link in between them, where you're iterating back and forth between doing your unsteady RAND simulation of a VOF model for the fluid flow, and then you're doing your finite element model for the structure. And this is tricky because there's a lot of effort that has to go into mapping back and forth between a 1D line model for a beam or frame element versus an actual solid mesh in 3D space that's in the CFD model. There's no direct way to couple them, so Nikki's work was primarily aimed at developing the means by which to transfer these loads back and forth between each other. So you'd start with the pressure from the fluid, you'd map it onto nodes that are on the mesh, and then they get mapped as forces onto the frame elements, and then the frame elements are deformed, and then you remap that back to get an updated geometry for the CFD model. And you just keep iterating like this until you converge every time step and just keep stepping through time. And so what we did with this was we did a validation with a flexible wall and a dam break model, which is sort of a classic thing to do. And we compared Nikki's foamy seas combo of open foam and open seas to StarCCM Plus and Justin's Claymore material point method code that he's been developing with Pedro Arduino. And yeah, to give a little bit more background on StarCCM Plus in terms of what I was doing with this. This is definitely something, and thinking what Barbara was saying, this is very much a two-way coupled problem, in my opinion. The structure is deforming so massively that the fluid flow is going to be redirected and vice versa, right? They're going to have a strong impact on each other. So you're not going to get a one-way coupled either fluid independent or structure independent situation here. To kind of give an overall map of how I would label something in the FSI world. And what is done in StarCCM Plus is you have a Lagrangian frame finite elements for the structure and Eulerian frame finite volume for the fluid. They used to have all finite volume, but the developers found that using finite element method is much more robust in general for the structure. So the code has been moved to do that instead. And this is all in one software. You can run these models together and do FSI all in one program, which simplifies things massively. Additionally, if you need to, you can use overset meshing, mesh morphing, remeshing, all kinds of different capabilities to distort the mesh here. And this is kind of a very extreme example I took from one of our, little marketing things where you've got a hummingbird's wing flapping. But yeah, in my case, I was using the RBF morpher. Yeah, and you can do just about anything in Star for FSI. Just kind of give an overview. What kind of applications are we actually doing in research and industry with this? Basically, the sky's the limit, I would say. So what kind of results did we get out of this? We got pretty good match between Wallhorn, which is an original all FEM monolithic solver for both the fluid and the structure that they created back in 2005. And then there's Nikki's Foamy Seas and my StarCCM Plus. And you can see qualitatively, at least, the free surface matches well at multiple times throughout the simulation, even during splashing on the wall. And giving it a bit of a close-up, the deformed shapes match quite well between, this is the StarCCM Plus result on the bottom, and then the original FEM result on the top. Some differences are found because they use different meshes. I used purely hexahedral meshing. I believe Nikki did the same. And then, yeah, they used tetrahedral for the fluid, which is not as robust, but it's again, it's a very standard practice in industry. How did the results for the deflection turn out? Pretty good, I would say. Everything overlapped quite well. The original result by Wallhorn was slightly lower than the Foamy Seas and StarCCM Plus results. The NPM code is a little bit higher, a little bit more flexible, as were several other PFEM codes that are compared here. But overall, we were very happy with the accuracy of all the codes lining up pretty good. And a little bit of additional findings we had were to get accurate beam deflections for such a flexible structure, you have to enable the nonlinear geometry option in Star, but you don't actually need to use higher order elements. You can get away with regular 8-node brick elements. And then Nikki also did some validation against some tests that were done at OSU against a concrete-filled steel tube column vertical evacuation structure. And again, there weren't displacement measurements coming out of that test in the same way as you would get from the numerical simulation, but the force measurement matched remarkably well. showing that this coupling method does indeed work quite well, and that this is while the displacement's not large, this FSI methodology can still reproduce basically what you'd get from like a pretty rigid boundary situation. And finally, the last thing I'll go over, Mike, let me know if I'm too short on time. Just to cover a little
quick on this one.
Yep, just to cover a little bit of what we've been doing most recently with Nils and Justin and company. Been modeling some debris being driven by a dam break wave impact from some tests that were done in Japan some time ago. And again, I'm taking a hybrid multi-phase approach, it'd be called, in STAR for this, where you can combine any of these numerical methods in any way you can imagine, but you want to pick something that depends on the applicable regimes. And so for a stratified flow with air and water, I went with the VOF method again, the volume of fluid. But then for the actual debris particles, I chose the discrete element method, which is better than the Lagrangian multi-phase method, which has point particles that can bounce off boundaries, but their actual radius does not matter, or their boundary does not matter. The DEM model is powerful enough, it can allow for arbitrary shapes. And so I was able to make rectangular blocks like in the original test. So some of the advantage of this is you can do very low fidelity compared to full FSI. You don't need to do a whole FEM solver. You don't need to do contact modeling in the same level of detail. So it leads to faster solution runs, and all kinds of interaction forces are very simple to model with this particle-based method. But the one big disadvantage I found was that the current implementation, at least in STAR, is that the VOF fluid interacting with the particles only occurs if the free surface passes through the center of gravity. If it doesn't, then it can flow through it as if it doesn't exist. So this will lead to a little bit of a reduced distance traveled, as I'll show in a couple slides. I'll skip my little video demonstration. So this is the wave basin we were modeling. I modeled the full thing, including the pressure valves. This tank in the back holds the water, and then it is released as the pressure valves are let go, and the wave translates across the domain. You can see here's a cross section of the mesh. So the water would be filling the reservoir at the left and then draining out under the sluice gate to create a dam break-like wave. And one thing I studied was it was a bit difficult based on the original paper to ascertain what the exact conditions were in the air valves versus the sluice gate. And so I did some study varying the height of the sluice gate as well as the pressure in the air valves. And we ended up settling all on the same height of the gate. And so then playing with the pressure in the air valve ended up helping get a more accurate free surface result down the line. And again, we got pretty good comparison between the SPH, MPM, and STAR CCM Plus across the board for different locations in the domain. Wave gauge 1 is the farthest offshore. Wave gauge 1 is onshore, past the structures, if I recall. And yeah, basically good results match. Here's a little bit of a depiction of how the particles moved in the STAR CCM Plus result. The main difference here is the SPH and the MPM ended up pushing them a lot farther because of the problem I was mentioning earlier, where the free surface must pass through the CG of these blocks to drive them, to impart momentum to them. So that ended up giving a bit of a detractor on the debris trajectories, but the forces and free surface heights were quite good. Again, one more comparison of the blocks as they impact the structures, they were blocking them. And then you can see these are the trajectories I got out of STAR, which compared to SPH and MPM, they went much farther out to, let's say, streamwise position 4 meters in a number of cases. So some work to be done there, maybe developing a custom field function to help them detect when the water is there, and an eventual update in the code. to just have that implemented directly. Yeah, thank you for your time.
Okay, thank you very much, Andrew. So I want to thank all three of our presenters today. I think this was a very useful discussion. I think that we have some time here on the back end to do a little bit of broader discussion. Andrew, you have a specific question there in the chat that's specific to your solver. And so if you want to kind of dive into that. But I do want to I want to go back. I think one of the questions in the chat that was answered on the front end, but Justin Bonus mentioned that past experiments don't account for advanced similitude scaling, especially with specifically with debris fluid structure interactions in their initial design. And I think all three presentations here started with an experimental discussion, right? I think we can't really avoid that. But oftentimes we're pulling from literature that the experiments took the data that they wanted, and then we kind of sort through that as best we can as modelers. And so Justin's question is, can we retcon some of this old data that limits some of the conclusions with new research so that we can continue to make this existing literature valuable? And Barbara, you answered that in the Q&A. So maybe if you wanted to just sort of quickly summarize your response to Justin, and that might spearhead something for the group here.
Sure. I mean, first of all, it's a really good question. I just want to say that for all of the SSI computational work that we've done, we've still always started with the rigid case where the structure itself is rigid. So that data is still super useful in sort of that initial validation part. The FSI effects, I think we need to be clear about what we mean by fluid structure interaction, because I believe people immediately go to, oh, there's this two-way coupling effect where the structural's response is affecting the fluid. And what we've seen is that, yes, but that's not always significant and oftentimes negligible. It just depends on the problem at hand. So, for example, it's not always the case that the structure deforms or vibrates, and then that affects the pressure conditions. It might affect the forces more, depending on where you're making those measurements. But it's not always affecting the quantities of interest from the fluid side. There are certain regimes where that two-way coupling does matter, and we need to identify where those regimes are. But it might be useful to also look at some of those coupling effects from a purely numerical standpoint as well. Like there's, I wrote this all down. I feel like it was much clearer when I wrote it. Now all my thoughts are jumbled.
Yeah.
But like I think like there's I guess in summary, I think there's 3 to 4 things that we can do. One is those rigid cases still get us a starting point for whatever CFD or FSI codes we have. 2, we need to identify whether it's one-way or two-way coupling based on the quantities of interest that we actually care about. And then 3, can we do everything numerically without the experiment? And is that believable? And that probably is a fidelity question, as well as like I think that's like very much a cultural perspective that we need experimental data. But like if we validate them both separately, like wind separately from waves, and then combine them, is that sometimes okay? And then 4 is like, can we go back to the old data sets and label them in such a way that they become more useful from that perspective? Like label them like, oh, this was incorporated. Oh, this was a sort of within this regime. And then add to those experimental data sets as needed. So clustering of thoughts.
Yeah. Nils, you had follow-up?
Yeah, I just wanted to comment on that question as well. And I'm speaking from my experience with my own data sets that we have published in the past, and then interacting with numerical modelers. One thing I noticed a lot that experimentalists sometimes are not good at really describing both sides. So the hydrodynamic and the structural part. And I say that especially because we had cases where people had asked the data from some of the experiments, and then while they were trying to model them numerically, we found that some of the original experiments were not described well enough for numerical modelers to make use of them. So, and Justin, when you were asking about whether we can make something out of those old experiments, sometimes it's tremendously difficult to kind of reiterate on what structural properties the structure set we were testing, or finding the right material constants, Young's modulus, and so forth. So I think this asks for much more collaboration between numerical modelers, structural and hydraulic engineers, in order to avoid these mistakes of not describing things well in your research papers, and making sure that everything is really, including all the materials and the structural drawings and everything, is recorded somewhere. This is something that makes working with old data sometimes, cumbersome.
Thank you. Thank you. Sort of building on that, I mean, this is something that many of us have been harping on for a number of years. I'd be curious to see from our panel or from anyone else in the audience, I mean, what is consistently missing, right? And so from the SimCenter's point of view, as we are trying to raise the profile of the various topics that we're using, and Barb, you mentioned getting to the point where we don't need experiments, and my guess is there was at least one person in the audience who gasped at that, because most of the time we get that. And so if we're going to be in this kind of this codependence, what can we say to the experimental folks out there and saying, like, these are the data that we crucially need as we start building out some of these models? And any answers from kind of anybody would be warranted here.
Yeah, and I'd love to hear from like other panelists and people in the audience as well. Just, I mean, the similitude thing everybody keeps harping on. I think we really need to think about what it means for these extreme loading conditions. And, whether that means doing an experiment multiple times with different scaling laws and different, like different dimensions, or whether it means actually making our structural specimens more realistic at small scale, or even like more field data at full scale. Like, I think that's like, if you can manage to sort of answer the similitude question first, then I think you can start asking some of these you can ask these interacting questions like second, right? I think they're kind of like coupled together.
Yeah. Okay, if Nils or Andrew has something to add there, but if not, we can kind of move on to the next discussion. So.
Yeah, I'm just intrigued to comment on whether we don't need experiments anymore. But I actually, just telling a short story. 20 years ago, when I was studying, I had a professor in coastal engineering, and he told us, look, numerical models are getting so good. In 5 years' time, we don't need experiments anymore. So this is now 20 years after he said that, and we are still trying to design the best experiments to answer our questions and help us verify numerical models. So I think it's always going to be a duality of numerical and experimental models. We can't avoid either.
No, I completely agree, and I think that we, even as the experiments start to play less of a role in the big picture, I think that having that background data there, and we're never going to avoid some level of skepticism by coming forward and saying, here's our 100% numerical result as well. So thank you very much. So Matt,
can I defend myself?
Sure. No, yeah, go for it.
Only because I totally agree with both of you. What I do think, though, is that this huge hesitation that we have for computational models without a complete experimental data set that describes every nuance of those computational models. I think we need to be careful about that. I think we're stuck in this thing that it's like, oh, but I didn't look at this exact shape in an experiment, and like there's no way for me to like extrapolate this model out like very close to the regime I started in. I think, you know, the days of that, I see quite a bit of hesitation on anything computational. And I think there's a local regime in which we can sort of extrapolate out a little bit if we have appropriate experimental data. And maybe some of that hesitancy is warranted, and I'm pushing an envelope that no one wants. But you know, they're quite, some of the numerical methods are quite good, and if you're able to understand how the physics sort of extrapolates, I think they're probably okay. But maybe I should.
I think you have a lot of supporters of that sentiment here. I think that you know, my experience with it is one, I completely agree. I think we can do all this stuff, and two, people don't believe us.
Yeah, exactly.
Yeah. So, okay. So, with that, I think we're gonna open the floor up to some more dialogue, but for the purposes of our kind of main attraction here, I want to thank Andrew and Nils and Barbara once again for 3 very interesting talks related to how we are modeling and bringing this tsunami and storm surge and kind of large wave modeling in from the ocean and the coastline to these individual structures as we reckon with how we're going to improve community resilience over the next few decades. And so thank you again. This was a wonderful trio of presentations. And so I very much appreciate your time and effort this morning.